This video is about branches. Given our discussion about multivaluedness in the previous video, you might now have the following question. In our definition of analytic functions, and that was given in topic 3. One of the conditions imposed is that they must be single valued. Therefore, does this mean we have to exclude things like the multivalued complex logarithm, complex powers that we also saw were multivalued at the end of the previous video, and roots? To answer this question, we're going to dig into the example of the square root function. Consider some complex function f of z, which is given by the square root of z. We're going to define this function as w. So w is a function of z. For some given instance of the complex number z, w is itself also a complex number. We can write that w squared equals z. We'll also write down some notation to make things easier later. We're going to write that the input z, written in modulus argument form and accounting for multivaluedness, is given by r e to the I and then theta plus 2n pi, where n is an integer. And we will also write that w can also be written in modulus argument form as r e to the I phi. Substituting these into our equation w squared equals z, we obtain that r squared e to the 2I phi equals r e to the I theta plus 2n pi. Let's now match the modulus and argument of the two sides of this equation. First of all, let's do the moduli. On the left-hand side we have r squared, and on the right-hand side we have lowercase r. So we have that r, capital R, is the square root of lowercase r, and I'll note here that we always choose the positive square root here, because we know that moduli of complex numbers are always greater than or equal to 0. Next, we can match the arguments of the left and right hand sides. On the left we have 2 phi, and on the right we have theta plus 2n pi, where we know that n is an integer. And this means that phi is theta over 2 plus n pi. We therefore have that the complex number w, we're now going to label with a subscript n, is given by r e to the I phi, which we have now shown is the square root of the modulus of z times e to the I theta over 2 plus n pi. I'll note here that n is the number of circuits that the vector z has made in the complex plane. In other words, it describes how many multiples of 2 pi the argument of z has acquired. Let's look at the different values of n and wn. If we set n equal to 0, in other words, z equals r e to the I theta, we have that w naught is root r e to the I theta over 2. If we set n equals 1, w1 is now the square root of r, and then e to the I theta over 2, and then we have a multiple of pi. We can take the factor of e to the I pi out the front as a minus sign, and this therefore gives us minus the square root of r e to the I theta over 2, which we recognise as minus w naught. Carrying on with increasing n, w2 is root r e to the I theta over 2, and we now have 2 pi. That factor of e to the 2 pi I is simply the number 1, and therefore we recover w naught. In other words, when n equals 2, the complex number z has made 2 full rotations in the complex plane, and we've recovered the original value of the complex number w. I'll write that down. Going around twice means we're back to where we started. And if we make another rotation, looking at n equals 3, w3, you can convince yourselves is minus w naught. And this kind of pattern will carry on where we alternate between w naught and minus w naught. What does this mean? This means that as theta of our complex number z goes from 0 to 2 pi, in other words, we rotate the vector for the complex number z about the origin once, w goes from being defined as the square root of the modulus of z to minus the square root of the modulus of z. In other words, you cannot just choose a sign for the square root function as we do for the real case. The freedom to rotate in the complex plane means that we can't make the same type of sign choice that we did previously. You can see that we hop from defining the number w as the square root of the modulus to minus the square root of the modulus. And that's simply by rotating the complex number z in the complex plane by 2 pi, which, whilst not changing the complex number z itself, does change the argument of z by 2 pi. We can delve a little deeper into this by looking at the action of the functions w0 and w1 separately. Let's first look at w0. Notice that w0, given by the square root of r e to the I theta over 2, as usual we can use Euler's formula to expand this out as cos theta over 2 plus I sine theta over 2. What do the real and imaginary parts of this look like as a function of theta? Let's draw some axes. We have theta, and then for convenience I'm going to label the numbers 1, 0 and minus 1. Let's first look at what happens to the real part of this number given by square root of r times cos theta over 2. I'm just going to be plotting the cos theta over 2 part. Well, this function is simply the cosine function, but stretched by a factor of 2 along the x-axis. So it's going to look like this. And I'll label the points of interest on the theta axis as pi and 2 pi. Next, let's plot the imaginary component given by sine of theta over 2. Again, this is going to be the sine function, but stretched by a factor of 2. I'll label these curves to make it absolutely clear that this is the imaginary component, and this is the real component, where we factored out square root of r. This is the whole range for the parameter theta, and crucially we see that the imaginary component of this complex number is always positive. I'll write that down here, that the imaginary part of w0, which is given by root r sine of theta over 2, is always greater than or equal to 0. Hence, for n equals 0, the function f of z is the square root of z, maps the entire complex plane in other words, the input to the function, into the upper half complex plane. To make this absolutely clear, we can draw a set of axes for the domain and range of our function. This here is the imaginary part of the input, the real part of the input. Below, I'll note that this is the domain to our function z, in other words, the input. And we can consider that theta equals 0 corresponds to just above the positive real axis, and theta equals 2 pi corresponds to coming from below on the positive real axis. The domain of our function is the entire complex plane. So I'm just shading to show that the whole complex plane is the input to our function. We're now considering the action of the function f of z given by w0, where we've set n equal to 0. We can give ourselves some axes for the output of our function. We have the imaginary part of w0, the real part of w0, and I'll label below that this is the range given by w0, in other words, the output. If we have the argument of z, theta equal to 0, then we get mapped onto the positive real axis. On the other hand, if we have theta equals 2 pi, then because of the factor of a half in z to the half, the output has argument pi. It gets mapped to the negative real axis. Therefore, the output of this complex function is limited to the upper half of the complex plane, which I'll shade here. What does this mean we can say about our function w0? Note, in particular, that w0 is discontinuous across the positive real axis of the domain or input to the function, because it changes by a sign. We can draw another picture to make this clearer. encoding the same information that we have in the plots above. We have the imaginary part of the input to our function, the domain, and the real part. This is the domain Z. And let's label what happens if we fix the modulus of some complex number, but rotate it around the origin. Well, over here, just above the positive real axis, we have theta equals 0, and therefore W0 is the square root of R. If we make a complete circuit and come back to just below the positive real axis, over here, well, now theta has gone from 0 to 2 pi, but the value that our function returns is minus the square root of R. And hence we have a discontinuity of 2 times the square root of R across the positive real axis. Let's now look at some properties of the function w when the label n equals 1. In other words, we've already made one full circuit around the origin in the complex plane for our input. We note that the final point, theta equals 2 pi, of the function we were just looking at, W0, is the initial point of the function W1. This is easy to see if we write out W1 is the square root of R e to the I theta over 2 and then crucially pi. We know from earlier that if we take out the factor of e to the I pi, this gives us minus W0. Setting theta equal to 2 pi for W0 gives the same result as setting theta equal to 0 for W1. What do the real and imaginary components of the complex number W1 look like? Well, it's just going to be a reflection about the x-axis of what we had earlier for W0. The real part is now given by minus cos of theta over 2, which looks like this. And the imaginary part is now minus sine of theta over 2, which looks like this. We therefore note that the imaginary part of W1 is less than or equal to 0. And so for n equals 1, our complex function, the square root, maps the entire complex plane to the lower half of the complex plane. Let's now stick W0 and W1 onto a single set of axes to have a final clear picture of what's going on. We're looking at the output of our function, the range, W. And we can label what happens for the different values of n on this single set of axes. This is the imaginary part, this is the real part, and I'm going to note over here that the input to our function z is r e to the I theta plus 2 n pi, for convenience to refer to in a moment. Let's imagine starting with the angle theta equals 0, and therefore the modulus of the complex number w is going to be given by the square root of r. Beginning with n equals 0, in other words, the function w0, we know that as theta varies from 0 to 2 pi, we're going to be constrained to the upper half of the complex plane. And I'm going to draw it as a semicircle with radius given by the square root of r, which executes this half circuit. I'll note that down here, this is when theta equals 2 pi, and we still have that the modulus is the square root of r. And this is what you get from the function w0 as you vary the argument of z from 0 to 2 pi. Once we've got theta equals 2 pi, in order to go any further, we now set n equal to 1 in that exponent. That means that we're going to move to the function w1. We can therefore reset the value of theta. So now we're thinking of theta equals 0, just below the negative real axis. And now w1 is going to map all of those complex numbers z to the lower half of the complex plane. Again, this will be described by a semicircle in the lower half complex plane, whose radius is given by the square root of r. I'll note over here that theta equals 2 pi. The modulus is still the square root of r, and this is what w1 does. It's therefore clear that the input z must go around the origin twice for w to return to the original value. Theta plus 2n pi has changed from 0 to 4 pi, and so taking into account the factor of 1/2 in our definition of the square root, w has changed by a factor of e to the 2 pi I. In other words, it has returned to its original value. We therefore note that our equation from earlier, w squared equals z, has no continuous single-valued solution w defined on the whole complex plane. Instead, this equation w squared equals z defines a two-valued function of z. We now get to a very important piece of terminology. The two functions w0 and w1 are called the branches of the solution f of z is the square root of z. These branches give rise to a discontinuity in the solution f of z is the square root of z. So how do we separate the two branches to stop crossing the discontinuity? We can make a branch cut along the line of discontinuity. So in this case, that means along the positive real axis. And this is a cut along the domain, in other words, the input to the function. I'm now going to plot the domain. Where this is the imaginary part of z, this is the real part of z. We're now going to cut the positive real axis, and I'm going to denote that by a zigzag line. In this case, extending off to plus infinity on the real axis. I'll note cut extends out to positive infinity on the real axis. This branch cut means that the input to our function can no longer make more than one full circuit in the complex plane. This defines the input to the branch of the function w0. Crucially, the input to our function now cannot pass this branch cut. So we can never cross over from the n equals 0 to the n equals 1 branch, because we can't go beyond one full circuit in the complex plane. I'll write that down here. We're now not allowed to cross to the W1 branch. As a result, the branch W0 is single valued for inputs that have theta between 0 and 2 pi. Similarly, for W1, the take-home message of what a branch cut does is we get self-consistency of the branches at the expense of a discontinuity at a cut we can never cross. And to make this specific, earlier for W0 we saw that just above the positive real axis, W0 was given by the square root of r, where r is the modulus of z, and the value of W0 for the complex number z coming just below the positive real axis was given by minus the square root of r. We therefore have a discontinuity of 2 times the square root of r across the branch cut for W0. I'm going to make a note about branch points. The origin, z equals 0, plays a special role here. Consider executing a closed path or loop C which does not contain the origin. We have the imaginary part and the real part. And our loop might look something like this, where we start here and we traverse in the anti-clockwise direction. We can think about the angle in the complex plane where we start And by tracking the line connecting the point on this closed loop and the origin, as we traverse around, we can see that the maximum value of the angle is going to be reached up here. And by the time we get back to our starting point, the angle is the same as it was at the beginning. I'll note that we start and end here. Therefore, this loop excursion does not add a phase of 2 pi to z. Therefore, for the function that we discussed earlier, we would, for example, remain on the W0 branch because there's no scope for making full circuits of 2 pi. Why is the origin special? Well, the point z equals 0 is singular, a notion that we encountered towards the end of the previous topic. The square root function does not have a derivative there, and so is not analytic at that point. You can check that with the Cauchy-Riemann equations or by differentiating z to the half directly. That'll give you a half z to the minus a half, and if you put in z equals 0, then that's undefined. The ambiguity in function value results from paths containing such a point. And this has a special name. We call such points a branch point. Of the function. I'll note that for the square root of z, z equals infinity is also a branch point and effectively defines the end of the branch cut that we make to define W0 and W1. And we'll revisit the concept of a branch point at infinity in the next video. Some more terminology. The order of a branch point is defined as the number of paths around it that must be taken before the function returns to its original value. The order of a branch point is defined as the number of paths around it that must be taken before the function returns to its original value. And we saw an example of this just now, that for z to the half, we saw that we had to make 2 full circuits to return to the branch we started on, and therefore we say that z equals 0 is a branch point of order 2. As a very quick sketch, imaginary part of z, and the real part of z we have to make an excursion that looks something like that to get back to the original value. A little bit more terminology before we look at some examples to finish. Regions that do not include branch points or branch cuts, or in fact other types of singularity we'll encounter later. Such regions are called simply connected. And we will see that this means that all loops in such a region can be continuously shrunk to a point. You may wonder why the branch cut we took was along the positive real axis. And in fact, it depends on how you define the principal values that the argument of a complex function can take. For example, we've taken it to lie between 0 and 2 pi, which then led us to take a cut along the positive real axis. But this is not unique. You could instead define the principal values of the argument between minus pi and pi. Your branch cut would then run along the negative real axis. We're going to be sticking with the principal values between 0 and 2 pi, and so the branch cut for the square root of z was along the positive real axis. There's been a lot of material in this video, but to finish it's very helpful to go through a couple of examples quickly. Let's begin by looking at the complex logarithm in its multivalued form. We saw this in the previous video, and we can write it as the ln of the modulus of z plus I lots of theta plus 2n pi, where n is an integer. Ln of z is singular at z equals 0. In particular, there's no derivative defined there. Because if you differentiate the logarithm of z, you get 1 over z, and this is undefined when z equals 0. Hence, we identify z equals 0 as a branch point of the function. It's clear from the definition as written that ln of z has an infinite number of branches. And that's true because any value of n gives you a completely new branch of the function. This means that, as earlier, it is not consistent to simply choose one branch. In other words, choose a single value of n. Because a full circuit typically in the anti-clockwise direction to increase n adds 2 pi I to the value of the function. And of course, this takes you to the next branches. For example, that would mean that the complex logarithm of the number 1 could be 0 or 2 pi I or 2n pi I, depending on which branch you've ended up on. A common way of visualizing this is using something called a Riemann surface. We'll need 3 axes for this. We have the real part of z, the imaginary part of z, and this is going to be the imaginary part of the multivalued logarithm of z. For some fixed modulus of z, rotations about the branch point z equals 0 simply add multiples of 2 pi I to the complex logarithm. If we start, let's say down here, when theta equals 0, then as we rotate z in the complex plane, the imaginary part of the logarithm does something like this. Where the radius of this spiral projected onto the xy plane is constant and given by ln of the modulus of z, but the imaginary part of ln of z increases as we rotate around. This first spiral defines the n equals 0 branch, the next spiral defines the n equals 1 branch, and this extends to plus and minus infinity above and below. And you can think of this as looking something like a multi-story car park. I'll note that these separate branches are sometimes called Riemann surfaces. In order to prevent passing between different branches and make the complex logarithm single-valued, we make a branch cut in order to remain on the n equals 0 branch. And as before, the branch cut here can be taken along the positive real axis from the branch point at z equals 0 up to infinity. We also define the complex logarithm of 1 to be 0 on this branch. As a second example, let's consider f of z is the square root of z minus 1. Well, this is a simple extension of our earlier discussion of the square root of z. The only difference is now z equals 1 is the branch point, where this function is singular. It's a branch point of order 2, while the point itself is unique. How we draw the branch cut is not. For example, we have our axes, and we have our branch point here at z equals 1. Earlier we had our branch cut running along the positive real axis, and I also mentioned that if we had instead defined the principal values of the argument as between minus pi and pi, then our branch cut would have run along the negative real axis. We could also have a branch cut like this, at some angle theta naught to the real axis. And this is completely valid if we remember to restrict the argument of z to lie between theta naught and theta naught plus 2 pi. But I'll again remind you that we will typically be cutting along axes. As a final example, Let's consider evaluating 1 to the power of I. There are a couple of ways of doing this. First of all, we might consider rewriting the number 1 as e to the 2 pi I. Raising that to the ith power means that we have e to the I squared 2 pi, which is e to the minus 2 pi. Alternatively, we could rewrite 1 to the power of I using our logarithm trick from the previous video. This would then become e to the I ln of 1, where let's assume we're taking the principal complex logarithm. This gives us the number 1. We note that these are not equal. So what's gone wrong? Well, in A, we treated e to the 2 pi I as a complex number with theta equals 2 pi. But crucially, this is outside the principal domain that we've mentioned a few times now of theta lying between 0 and 2 pi, where 0 is inclusive and 2 pi is exclusive. This is particularly clear using the multivalued logarithm in part B. We would have that 1 to the power of I is e to the I multivalued logarithm of 1, which gives us e to the I times 2n pi I, e to the minus 2n pi. Therefore, we note that A, we have implicitly constrained ourselves to the n equals 1 branch, whereas on B, we've stayed on the n equals 0 branch. That's the end of this second video of topic 4, and we've covered a lot of material in this video. We've seen that multivaluedness gives rise to branches of a function. The example of the square root function gave us 2 solutions to the equation w squared equals z. By rotating the input z around the origin multiple times, we saw that we could alternate between w0 and w1 branches. These map the whole complex plane to the upper and lower halves of the complex plane, respectively. We saw how a branch cut along the line of discontinuity, in this case the positive real axis, allows us to define a single-valued solution to the equation w squared equals z. This limiting of the input values to a function gives us self-consistency, but at the expense of a discontinuity at a branch cut that we can never cross. We saw that for the square root, the origin z equals 0 plays a special role. Loops that don't enclose the origin don't give rise to jumping between branches. We call z equals 0 a branch point, which is a singularity where the function fails to be analytic. We then defined the order of a branch point as the number of paths that must be taken around it, so the function returns to its original value. We finished by looking at a couple of examples, including that of the complex logarithm, and how to take a branch cut to make it single-valued. Thanks for listening to this video. Next up is the third video of topic 4.